Look up at the night sky and you see a calm scattering of stars, but you are standing inside a machine you were never told existed. For 13 billion years, the Milky Way has been running invisible systems that shape what lives, what dies, and what gets to keep its fuel. Here is the paradox. Our galaxy looks like a simple spiral, yet it quietly behaves like it has defenses, not against aliens, not against magic, against physics itself turned into protection. And we only started noticing because different teams kept finding the same weird fingerprints in the data. Stay with me, because once you see the pattern, you cannot unsee it. And if you like this kind of deep, true cosmic mystery, like the video and subscribe. For most of human history, a galaxy was just a picture in the mind. A city of stars held together by gravity, drifting through emptiness. Even after telescopes got better, and we learned the Milky Way was a barred spiral, our mental model stayed simple. Stars, gas, dust, a central bulge, elegant arms, rotation, like a slow carousel. Beautiful, yes. Complicated, sure, but still basically a single idea. Then the last decade arrived and quietly embarrassed us. Between 2013 and 2025, astronomers working on completely different problems kept stumbling into the same kind of surprise. One team would be measuring ultraviolet light near a pair of dwarf galaxies. Another would be mapping gamma rays near the galactic center. Another would be collecting cosmic ray events over years and noticing patterns that refused to be random. At first, these stories looked separate. Different instruments, different wavelengths, different corners of the sky. But slowly, a larger picture emerged. Our Milky Way has protective structures. Real physical phenomena that behave like barriers, buffers, and filters. Not force fields, not science fiction shields. These are made of hot gas, magnetic fields, dense rings of matter, and the motion of material through space. They are invisible to your eyes, but they leave signatures in the light and particles we can detect. And once you understand them, the galaxy stops looking like a simple spiral made of stars. It starts looking like an ecosystem. In this story, we are going to follow three major discoveries. Each one lives in a different region of the Milky Way, and each one answers a different threat. The first one sits out in the suburbs of our galaxy, around two small companion galaxies that have no business still being alive. The second sits at the very heart of the Milky Way, around the supermassive black hole that should be flooding space with deadly particles. The third lives at the edge, where our galaxy fades into the wider universe, and incoming particles behave as if they are being sorted by an unseen border. And we are going to do it the human way, with clear language, simple comparisons, and a shared sense of detective work. Let us start with the kind of mystery that makes scientists uncomfortable, because it is not a subtle discrepancy, it is a basic contradiction. Two small galaxies sit right next door to us, and the numbers say they should be dead. The Large Magellanic Cloud and the Small Magellanic Cloud are not distant smudges on a deep space photograph. From the southern hemisphere, you can see them with your naked eyes as fuzzy patches of light. Ancient sailors used them like cosmic landmarks. In the scale of the universe, they are basically our neighbours. The Large Magellanic Cloud is about 160,000 light-years away. The Small Magellanic Cloud is about 200,000 light-years away. That is close enough that their relationship with the Milky Way is not a rumour. It is an ongoing interaction, and it is a rough one. When a small galaxy wanders too near a large one, gravity is not the only problem. People tend to imagine gravity like hands pulling on stars, but gravity also pulls on gas. And gas is the lifeblood of a galaxy. Gas is what you turn into new stars. Take away the gas and a galaxy becomes a museum. Beautiful, full of old light, but unable to make anything new. Now add motion. The Magellanic Clouds are moving through the outer regions of the Milky Way environment at roughly 400 kilometers per second. That is not a poetic number. That is a physical circumstance. Moving through a thin medium at high speed creates a kind of pressure. In space it is called ram pressure. A simple mental picture is sticking your hand out of a car window on the highway. Air becomes a force. Now replace your hand with a loose pile of sand. The wind would tear it away. A small galaxy is not a pile of sand, but its gas can behave that way. The Milky Way has a diffuse halo of gas extending far beyond the bright disk of stars. When the Magellanic Clouds plough through that halo, the halo pushes back. It should peel their gas away. It should strip them down over time, leaving a trail. We actually knew about that trail long before we understood the shield. It is called the Magellanic Stream, a river of hydrogen gas stretching across the sky, trailing behind the clouds along their orbit. The very existence of that stream proves stripping is happening. So here is the contradiction. If stripping has been happening for billions of years and the clouds are moving fast, why are they still forming stars today? Why do they still have so much gas? Why do we see bright regions of young stars instead of a quiet, exhausted relic? In 2013, astronomers were not hunting for a galaxy shield. They were doing normal science. They were aiming the Hubble Space Telescope at the region around the Magellanic Stream, trying to understand where the stripped gas came from and how it behaved. They used ultraviolet observations because ultraviolet light is a special kind of clue. It can reveal hot gas that does not show up in ordinary visible images. What they found did not immediately scream shield. It was more like an odd glow, a signature that suggested extremely hot material was present where it should not be obvious. Over the years, more teams joined in, different telescopes, different methods, different wavelengths. Like detectives comparing notes, each new measurement did not replace the previous one, it stacked on top of it. Then the picture sharpened. There was a massive envelope of superheated gas surrounding both Magellanic Clouds. A bubble, or corona, heated to roughly 1 million to 2.5 million degrees. That is not the temperature of an atmosphere or a campfire. At those temperatures, atoms move so fast that collisions can produce ultraviolet light and even X-rays. The gas is thin and spread out, which makes it dim, but it is real, and the scale is what makes your brain trip. The bubble extends on the order of 100,000 light-years around those small galaxies. For comparison, the Milky Way disk of stars is about 100,000 light-years across. Two little neighbor galaxies are wrapped in a structure comparable in size to our entire visible galaxy. So what is it doing there? The most important clue is that this bubble is not something placed around them from outside. It is something they generate. The same motion that should strip them also heats their outer layers. Some of their own gas gets compressed and heated as they push through the Milky Way halo. Hot gas is less dense than cooler gas. It acts like a cushion, a buffer zone. Imagine you are riding a motorcycle at extreme speed through thick fog. The fog is the Milky Way halo gas. At that speed, the fog would hit you like a wall. But now imagine that in front of you is a smooth, invisible shape that takes the hit first, pushing the fog aside. The fog still exists, the threat is still there, but the impact is redirected away from the fragile core. That is what the million-degree corona does. It takes the punishment. It does not stop stripping completely, it slows it. It turns what should have been a quick execution into a slow leak. Without it, the clouds should have lost their gas long ago. With it, they can survive for billions of years, long enough to keep forming stars, long enough to remain lively neighbors instead of dim ghosts. And here is the delicious irony. The shield is powered by the very attack it is shielding against. Motion through gas creates heating. Heating creates a buffer. The buffer reduces stripping. Physics turns danger into defense. At first, the community was skeptical. Early evidence was indirect. Ultraviolet signatures can be tricky. Maybe the signal came from other sources. Maybe young stars were contaminating the measurement. Maybe the halo gas of the Milky Way itself was responsible. But then X-ray observations, especially from Chandra, piled on the confirmation. Hot gas at the right temperatures, in the right place, with a shape that matched the idea of a protective envelope. A ghost becomes a thing. Now pause and let that sink in, because we are going to build on it. You are living in a galaxy where two nearby dwarfs are not just being eaten. They are being eaten slowly, regulated by a huge hot cushion that exists because of motion, heat, and the way gas behaves on cosmic scales. A bubble the size of a galaxy glowing in invisible light, wrapping around two small companions like a helmet in a storm. And that is only shield number 1, because as strange as it is to find a million-degree envelope protecting neighbouring galaxies, it is nothing compared to what we find at the opposite extreme. Deep in the centre of the Milky Way, where a supermassive black hole sits in a crowded, violent environment, we find a different kind of barrier. A barrier that prevents one of the most dangerous kinds of radiation from flooding outward and turning the inner galaxy into a slow sterilization experiment. We are going there next. The Magellanic Clouds are the kind of objects that feel harmless. Two soft smudges, two little companions. But in galactic terms, they are not ornaments. They are bodies in motion, carrying reservoirs of gas, and they are crossing into the territory where big galaxies eat small ones slowly, inevitably, and without mercy. If the Milky Way were a vast city of light, the Magellanic Clouds would be towns on the outskirts, close enough to visit, close enough to influence, close enough to get trapped. The Large Magellanic Cloud sits roughly 160,000 light-years away. The Small Magellanic Cloud is closer to 200,000 light-years away. That is not across the universe, that is across the neighbourhood. And the neighbourhood has weather. Galaxies are not just stars. The space between stars is filled with gas, dust and plasma. Some of it is cold enough to collapse into new stars, some of it's hot enough to glow in invisible wavelengths. And around the Milky Way, far beyond the bright spiral disk, there is a halo of thin gas that extends like an atmosphere stretched across hundreds of thousands of light-years. Now picture two smaller galaxies cutting through that halo. Their speed relative to the Milky Way environment is roughly 400 kilometers per second. That number matters because it turns a thin haze into a stripping force. It is the same reason you can walk through mist and feel nothing, but race through air fast enough and suddenly it becomes pressure, friction, resistance based in a not empty space enough to ignore when you're moving at that kind of speed. This is where the grim mechanism enters. Ram pressure stripping is the phrase astronomers use, but the idea is brutally intuitive. A galaxy does not hold on to gas the way a planet holds on to air. Gas in a galaxy is spread out. It is loosely bound. It is constantly stirred, heated, cooled and pushed around by radiation, shock waves and star formation. When a small galaxy moves through the diffuse gas of a larger galaxy's halo, the external gas pushes against the small galaxy's own gas. It is like wind pushing water out of a shallow bowl. The bowl is the small galaxy's gravity. The water is the gas that would form future stars. If the wind is strong enough, it does not need to shatter the bowl. It just needs to peel off the water layer by layer. Over time, the bowl still exists, but it becomes dry. A galaxy without gas becomes a place where star formation dies out. Bright blue young stars stop appearing. The population ages. The galaxy turns redder, dimmer, quieter. That is what the equations predict for satellites like these. And it is not just prediction, by analogy. Astronomers have seen this process in many galaxy systems. In clusters of galaxies, where the space between galaxies is filled with hot gas, you can watch ram pressure stripping long tails of gas out of smaller galaxies like streamers behind a speeding car. The smaller galaxy keeps its stars but loses the raw material that would have made new ones. So why are the Magellanic Clouds still lively? This is the part where the universe gets cheeky. Because the sky itself contains evidence that the stripping is real. There is a trail, a river, a ribbon of hydrogen gas arching across a huge fraction of the sky, the Magellanic Stream. Even before we understood the protective bubble, astronomers knew something was being removed from the clouds. The stream is a signature of loss. It says the Milky Way is not passively hosting these companions. It is actively pulling material away from them, leaving a wake behind their orbit. That should have been the end of the story. Stripping creates a tail grows, gas runs out, star formation shuts down, except it did not. The Large Magellanic Cloud is still making new stars right now, not in some vague historical sense, but currently actively, constantly. On average, it is forming roughly half a sun's worth of new stars each year. That might sound small until you remember what it implies. Star formation requires dense gas clouds. Dense gas clouds require a supply. A galaxy cannot keep doing that for billions of years if it is being stripped at full speed with no protection. So the contradiction becomes sharp enough to cut you. If the stripping is strong enough to create the Magellanic Stream, why has it not already emptied the clouds? Why do they still have enough gas to sustain star formation? Why are they not dim fossils? You can feel the tension building here because this is not a detail. It is a basic question about survival. If we cannot explain why these satellites still breathe, we do not understand how small galaxies persist near big ones. And that problem is bigger than our backyard. It shapes how galaxies evolve across the universe. This is why those ultraviolet observations mattered so much. Astronomers went looking for clues in the region between the Magellanic Clouds and the Milky Way. They were not hunting for a shield, they were trying to understand the environment. Ultraviolet light is useful because it can reveal gas that is far hotter than anything you can see in normal images. Not the heat of a star's surface, but gas heated so intensely that its atoms are smashed into states that produce distinctive ultraviolet signatures. When you detect ultraviolet light coming from the space around a galaxy, you're often seeing a fingerprint of hot gas that is otherwise invisible. So the question becomes, what kind of hot gas is sitting there, and why? If there is no special structure, you would expect the Magellanic Clouds to be directly exposed to the Milky Way halo. Like bare skin in a storm. You would expect gas to be pulled away more efficiently. You would expect star formation to collapse faster. In other words, you would expect the math to win. But the universe is not obligated to respect our first draft of the math. The universe only respects physics, and physics sometimes creates unexpected cushions. The deeper you push into the details, the more you realize the Magellanic Clouds are not just drifting in a void, they are embedded in a flow. They are interacting with a medium. Their motion compresses gas. Compression heats gas. Heated gas behaves differently than cool gas. It becomes less dense, more energetic, harder to grip. Even before anyone confidently said bubble, the data was already whispering something like it. A broad, diffuse region of hot material, not concentrated in a point, not tied neatly to star-forming regions, something large, extended, and strangely placed. And that is where the emotional shift happens. The Magellanic Clouds stop looking like doomed prey, they start looking like survivors. Not because they are strong enough to resist the Milky Way's gravity. They are not. Not because they are hidden. They are not. But because the interaction itself seems to generate a buffer that changes the rules of the stripping game. A thin layer that takes the hit first. A region where the external pressure meets hot, energized gas instead of directly clawing at the cold star-forming fuel. If this is true, it would explain everything all at once. The stream exists because stripping still happens. The clouds live because stripping is slowed. The contradiction dissolves, but only if you accept a new idea that feels almost too convenient. A protective envelope of hot gas surrounding the two galaxies. And the only way to be sure is to see it, not with eyes, but with the wavelengths that hot gas cannot help but reveal. That is what we do next. We follow the evidence from faint ultraviolet hints to the hard confirmation in X-rays, and we meet the structure that changes the fate of two galaxies. A million-degree corona as big as the Milky Way disk, glowing silently around our nearest companions. If you want to understand how strange this discovery is, you have to imagine what the scientists were actually trying to do. They were not pointing a telescope at the Magellanic Clouds and asking, is there a giant shield around them? They were chasing a different puzzle, the Magellanic Serpentine Stream, that long trail of gas that proves the Milky Way is stripping material away. They were looking for the source of the stream, how it forms, how it survives, how it connects to the clouds. Normal, responsible astronomy. And then the data did that thing it loves to do. It started whispering a second story in the background. The whisper came in ultraviolet light. Ultraviolet is awkward because it is invisible to your eyes, and because it is picky. Space does not just glow in ultraviolet for no reason. You usually need very specific conditions, like gas heated until its atoms are battered into excited states, or gas so thin and energetic that it announces itself through faint signatures rather than bright shapes. So when Hubble saw ultraviolet clues in the region around the Magellanic Clouds, the immediate reaction was not, we found a shield. The immediate reaction was, what is making that light? The phrase hot gas does not do it justice, because our brains think hot means a stove, a fire, a desert day. Here we are talking about gas heated to more than 1 million degrees, sometimes closer to 2.5 million degrees. At those temperatures, atoms are not politely drifting, they are racing. They slam into each other hard enough to kick out energy in ultraviolet and even X-ray wavelengths, and that's the first key point. You do not see this bubble in a normal picture of the sky, because it is not made of dense stars. It is made of thin plasma spread across an enormous volume. It is a glow, not a spotlight. A neon sign, but in a colour your eyes cannot access. For several years, the evidence was suggestive rather than definitive. Scientists could detect ultraviolet signals and infer that hot gas existed, but inference is not the same as measurement. The skeptical voice in every good scientist says, maybe you are seeing something else. Maybe it is ultraviolet from young stars inside the Magellanic Clouds. Maybe it is gas that belongs to the Milky Way halo itself, just happening to sit in that direction. Maybe the analysis is too indirect, that skepticism mattered, because a claim like this is not a small claim. A hot envelope around two dwarf galaxies would rewrite the timeline of how long satellites can survive around larger hosts. It would explain why the clouds are still forming stars, but it would also imply that many other satellite galaxies may have similar protection, hidden only because we did not have the instruments to see it. So the hunt continued, and the next clue came in a harsher language: X-rays. X-rays are produced by even hotter gas than the kind that shines in ultraviolet. If there really was a huge region of million-degree plasma wrapping the Magellanic Clouds, it should not just whisper in ultraviolet, it should glow, faintly but measurably, in X-rays. Between 2019 and 2020, multiple teams used the Chandra X-ray Observatory to study the same region and ask the bluntest possible question: is there hot gas where the bubble theory says it should be? The answer came back as yes. Gas heated to above 1 million degrees was detected around the Magellanic Clouds, and it was not a tiny local patch. It matched the idea of an extended envelope. It fit the predicted shape. It carried the right kind of signal. The bubble stopped being a clever explanation and became a measured structure. This is where the scale hits you in the chest. The hot envelope extends at least about 100,000 light-years in every direction around those dwarf galaxies. For comparison, the Milky Way disk of stars is about 100,000 light-years across, so you have two small companion galaxies, each far smaller than the Milky Way, surrounded by a structure comparable in size to the Milky Way itself. That is why people started calling it a corona. Not because it is a halo in the visual sense, but because it is an envelope of hot plasma surrounding a system, like an atmosphere around a world, except stretched to galactic proportions. Now we have to answer the most important question: how does a bubble of hot gas protect anything? The key is that stripping is not just about gravity tugging at gas. Stripping is about direct impact. It is about the external medium ramming into the gas reservoir of the smaller galaxy, shredding it over time. If you can create a buffer layer, you can change the nature of that impact. Hot gas is less dense, it is more energetic. Its particles move incredibly fast, on the order of thousands of kilometers per second. That does not mean the bubble is a solid wall. It is more like an airbag that inflates in slow motion. It spreads out the force, it takes the initial collision, it reshapes the flow. So instead of the Milky Way halo slamming directly into the cool, dense gas where stars are forming, it slams into a region of hot, thin plasma first. That hot plasma resists being cleanly peeled away. It is energetic enough that it behaves differently under the same forces. It is also positioned like a sacrificial layer, taking the punishment that would otherwise tear into the galaxy's star-forming core. You can picture it like a teardrop-shaped wake around a moving object. The leading edge faces the oncoming flow and gets compressed. The trailing edge is more vulnerable and more likely to leak. That detail matters because it fits what we observe. The Magellanic Stream exists, and it trails behind. The bubble is not perfectly sealed. It is a protective layer with weak spots. This is what makes the story feel less like a fairy tale and more like physics. Real protection is rarely absolute. It is moderation. It is control of rate. It is buying time. With no buffer, the clouds should have lost their gas rapidly, faster than what we infer today. With the buffer, the stripping becomes slower, stretched out over billions of years. Enough time for the clouds to keep forming stars in the present day. Enough time for them to remain complex, living systems rather than dead light. And then there is the most poetic part, and also the most ruthless. The corona is powered by the threat. The Magellanic Clouds are moving fast through the Milky Way environment. That motion compresses and heats gas, heating creates the corona. The corona slows the stripping. The very process that should kill them also builds the layer that keeps them alive longer. The galaxy turns attack into defense, not through intelligence, but through basic laws acting on an enormous scales. By around 2020, the combined evidence became hard to ignore. Different instruments, different wavelengths, different teams, all pointing toward the same conclusion. The Magellanic Corona is real, it is measurable, and it behaves like a shield. So now we have a new picture of our neighborhood. The Milky Way is not simply eating its companions, it is eating them slowly, and the pace is regulated by a vast, invisible envelope of hot gas that wraps around them like a cosmic buffer. But a shield should leave a signature you can see, not with eyes, but with the right kind of vision. And that signature had been in the sky for decades, waiting for us to understand what it really meant. That signature is the Magellanic Stream, the long river of hydrogen gas that proves the bubble is not just present, it is doing work. We follow that river next. A shield is easiest to believe when it leaves a mark. The Magellanic corona is an invisible cushion of million-degree gas, which means you only find it by catching faint ultraviolet and X-ray fingerprints. But the story of the Magellanic Clouds has always had a more dramatic clue written across the sky, a structure so large it is almost comical that we discovered it by accident. The Magellanic Stream. It is a ribbon of hydrogen gas trailing behind the Magellanic Clouds, wrapping around the Milky Way like a streamer, caught in a slow cosmic wind. If your eyes could see radio waves and you stood under a dark southern sky, you would not just see stars. You would see a huge glowing arc stretching across more than half the sky, a river of gas, flowing not for thousands of kilometers, not for millions, but for hundreds of thousands of light years. And the wild part is that astronomers stumbled into it back in 1974. They were using radio telescopes in Australia to map neutral hydrogen in the southern sky. Neutral hydrogen is the simplest atom, just one proton and one electron, and it emits a very specific radio signal. Astronomers love it because it lets them trace gas even when it is cold and dark and invisible in normal light. You can map where the raw material for stars is hiding. So the team was surveying hydrogen patch by patch, building a map like a cartographer mapping an unseen ocean. When they pointed their instruments near the Magellanic Clouds, they expected to see the clouds themselves, bright in hydrogen because they carry so much gas. They did see them, but they also saw something else, a faint extension, a trail. At first it could have been noise, interference, a glitch, but it did not go away. Every time they looked, the signal was there. With careful processing, adjusting contrast the way you might adjust shadows in a photograph, the faint trail became a coherent structure, a long arc of gas, originating near the clouds, stretching away along their orbit. That was the first time humans realized these little neighbor galaxies were leaving a wake behind them. Over the decades, as radio technology improved, the stream became clearer. It did not shrink into an artifact. It grew into one of the largest structures associated with our galaxy. Today, the rough numbers are hard to hold in your mind, which is usually how you know you are dealing with something real in astronomy. The stream stretches for about 600,000 light years. Light travels fast, about 300,000 kilometers per second, but even at that speed, light would take roughly 600,000 years to cross the full length. If you started the journey when the earliest modern humans were emerging, you would still have almost the entire trip ahead of you. The stream is also not a vague haze. In many regions, it is relatively narrow compared to its length, on the order of tens of thousands of light years across, which makes it feel like a ribbon rather than a fog. It really is a river shape. It traces the orbital path of the clouds around the Milky Way, and it contains a staggering amount of gas, roughly on the order of billions of suns in hydrogen, enough raw material to build billions of new stars if it ever gets compressed and recycled into star-forming regions. So the stream answers one question immediately. Yes, stripping is happening. The Milky Way is pulling gas away from the clouds. They are not floating peacefully, they are being harvested. But the stream also creates a new problem, and it is the same contradiction we started with, now sharpened into a blade. If the stream has been forming for billions of years, why are the clouds not empty by now? You would think a structure that huge implies a violent, efficient stripping process. You would imagine the clouds bleeding gas into the wake like a punctured tank. If that were true, star formation in the clouds should have crashed long ago. The stream should be even bigger, and the clouds should be dry, yet they are not. This is where careful measurement becomes the judge. Astronomers did not just map the stream's shape. They measured its mass, its density, its velocity, and how those properties change along its length. They asked how quickly gas is being added to it. They asked how old different segments are based on how far the gas has travelled. They asked whether the stream is smooth or clumpy, whether it splits, whether it fragments. And the surprising result is that the stream is enormous, but it is not enormous enough. That sounds like a joke, but it is a scientific clue. If the clouds were stripped at the full expected rate, the stream should be much larger, and the clouds should be far more depleted than they appear. The stream exists, which means stripping is real, but its scale relative to the cloud's remaining gas suggests the stripping has been slowed down. In other words, the stream behaves like the record of a wound that is bleeding slowly, not a wound that is bleeding out. This is where the corona becomes more than a pretty idea. The stream is the proof that the corona does not stop stripping, it regulates it. It acts like a buffer that reduces the rate at which gas can be removed from the clouds. Without that buffer, the wake should be thicker, longer and more massive. The clouds should have shut down. Instead, what we see is consistent with a controlled leak. Now take a step closer to the details because they make the story feel real. High-resolution mapping, including major radio surveys in the last couple of decades, revealed that the stream is not a single smooth rope. It has structure. Clumps, filaments, regions where it splits into substreams. That is exactly what you expect when gas is being pulled out in a complex environment, mixing with halo gas, cooling in places, heating in others. It also tells us something about time. The oldest sections of the stream appear to be roughly 2 to 2.5 billion years old. That matters because it anchors the timeline. It suggests the clouds have been interacting with the Milky Way environment for at least that long. It also suggests the corona has been operating for at least that long, because the stream is the long-term consequence of the same interaction the corona moderates. This is where another old debate quietly changes shape. For a long time, astronomers argued about whether the Magellanic Clouds are newcomers making their first pass around the Milky Way, or long-term satellites that have been circling for multiple orbits. A multi-billion-year stream tilts the scale toward a long relationship, not a first date, a long, complicated marriage. And that makes the corona even more impressive. A protective envelope of million-degree gas that persists for billions of years is not a fleeting accident. It is a stable feature produced by ongoing motion, constantly maintained by the same ram pressure that threatens the clouds. So now we have a paired system. The corona is the invisible bandage. The stream is the visible scar. The scar proves the injury. The bandage explains why the injury is not immediately fatal. And this is where the story starts to turn philosophical, not in a woo way, but in a cosmic ecology way. Because the stream is not just loss, it is transfer. Gas stripped from the clouds does not vanish. Over long timescales, much of it will fall into the Milky Way and join our galaxy's own reservoirs. It can cool, it can collapse, it can become new stars, it can seed new planetary systems. The clouds are being eaten, but they are also feeding the Milky Way, slowly regulated over billions of years. That means the corona is not just saving the clouds from a quick death, it is also smoothing the feeding process for the Milky Way, turning what could be a chaotic gulp into a slow meal. Less disruption, more stability, and that is the key idea we carry forward. These shields are not separate curiosities. They shape the entire galactic ecosystem. They regulate flow, they moderate extremes, they create longer windows of time for stars and planets and maybe life to exist. Now we leave the outskirts and travel to the opposite extreme, into the crowded core of the Milky Way. Because if you think a hot bubble protecting two dwarf galaxies is strange, wait until you meet the barrier that keeps the galaxy's center from blasting the rest of the Milky Way with high-energy particles. A bubble that large raises an uncomfortable question. Heat does not like to sit still. Hot gas expands. Hot gas cools. Hot gas leaks. So how do you keep an envelope of million-degree plasma wrapped around two dwarf galaxies for billions of years without it fading away like breath on a mirror? The answer is almost annoyingly simple. Motion. The Magellanic Clouds are not parked. They are cutting through the Milky Way environment at a speed that turns thin gas into a constant source of heating. The same ram pressure that wants to strip them also compresses the outer layers of their own gas. Compression raises temperature. Collisions become more violent. Energy moves into the plasma, and that energy keeps replenishing the corona. It is a little like a meteor entering Earth's atmosphere. The meteor does not burn because space is hot. It burns because it is moving fast through gas. Friction is not quite the right word in the microscopic sense, but the effect is familiar. Fast motion through a medium converts kinetic energy into heat. The Magellanic Clouds are doing a slow-motion version of that on a scale that is hard to picture. This is where the corona stops feeling mysterious and starts feeling inevitable. If you move a gas-rich system through a larger galaxy's halo, some gas will be heated, If some gas is heated enough, it becomes a thin, energetic buffer. If a buffer exists, it changes the stripping dynamics. A feedback loop forms. The threat helps sustain the defense. But feedback loops have moods. They only work inside certain conditions. If the clouds were moving much slower, they would not generate enough heating to maintain a strong hot layer. The buffer would be weaker, cooler, less effective. Stripping would bite deeper. Star formation would decline sooner. If they were moving much faster, the pressure would rise to the point where even a hot layer could not take the hit. The buffer would be overwhelmed. Gas would be torn away faster than it could be heated into protection. Instead, the clouds appear to sit in a kind of balance. Fast enough to create the shield. Slow enough for the shield to matter. It feels like luck, but it is really selection. Systems that land outside that balance do not stay around long enough for us to admire them. The survivors are the ones whose orbits produce long-lived, stable interactions. And that idea is bigger than the Magellanic Clouds. It suggests that many dwarf galaxies orbiting big galaxies may have their own invisible coronas. We simply did not have the tools to detect them until recently. If that is true, then a lot of older models that predicted rapid stripping may have been missing this self-generated cushion. The universe was not contradicting itself. We were missing a piece. Now, borrowed time is still borrowed. The corona slows stripping, it does not stop it. The Magellanic Clouds are losing gas. The stream exists because loss is real. The buffer is like a break, not a wall, so the long-term fate does not change in direction, only in schedule. Over billions of years, the clouds will run down their tank. The Milky Way's gravity will keep tugging. The outer layers will keep shedding. Star formation will gradually become harder. The bright stellar nurseries we see today will fade as fewer dense clouds survive long enough to collapse into new stars. On a timescale of several billion years, they will become quieter galaxies. Still full of stars, but increasingly dominated by older populations. Eventually, they will be dark in the sense that they will no longer be creating new stars in meaningful numbers. They will be fossils, not because they vanish, but because they stop evolving in the most dramatic way a galaxy can. And yet, even that ending has a strange kind of generosity. The gas that leaves the clouds is not destroyed. It does not evaporate into nothing. It becomes part of the Milky Way environment. Over long timescales, much of it can fall inward, cool, and join the reservoirs of gas that form new stars in our galaxy. So the clouds are not only being consumed, they are feeding the Milky Way, not in a violent gulp, but in a slow transfer that can be gentle on galactic scales, a steady infusion rather than a disruptive dump. The corona helps regulate that flow, which may matter more than it sounds. Galaxies are delicate in their own way. Too much gas arriving too quickly can trigger chaotic bursts of star formation, followed by long exhausted lulls. A slow supply can maintain steadier behavior over time. Now zoom into the human level for a moment, because this is where the story gets quietly emotional. Every atom in your body has a history. Hydrogen is ancient, dating back to the early universe. Carbon, oxygen, silicon, iron were forged inside stars and scattered by stellar deaths. Those atoms drift through space, join clouds, collapse into new stars, get thrown out again, and recycle over and over. The Magellanic Stream is part of that recycling. It is a visible conveyor belt of raw material moving from one galaxy into the larger ecosystem of another. If that gas forms new stars in the Milky Way in the far future, then some of the planets around those stars will be built from atoms that once lived inside the Magellanic Clouds. If life ever arises on any of those worlds, its chemistry will include atoms that travelled across hundreds of thousands of light years, carried by a river of hydrogen we can map today. That is not destiny, it is probability. It is the universe doing what it does, shuffling matter across vast distances and long timescales, letting complexity emerge wherever conditions allow it. And the corona is part of those conditions. It does not exist to help life. It exists because hot gas behaves like hot gas, because motion through a medium creates heating, because plasma forms buffers, because gravity and fluid dynamics do not care about our expectations, but the effect is still profound. A shield that buys time is not just delaying death. It is extending the window where stars can form, where planets can assemble, where chemistry can run long enough to get interesting. So out in the Milky Way suburbs, Two dwarf galaxies are living on borrowed time. Their shield is real, their wound is visible, and their future is a slow donation to the galaxy that is consuming them. Now we pivot from slow to intense. Because the next shield lives in the most crowded, energetic environment in our galaxy. A place where the danger is not stripping, it is radiation. Particles accelerated to nearly the speed of light, capable of punching through DNA and electronics and atmospheres. A place where, by all rights, the Milky Way should be leaking a storm of cosmic rays into its own disk. And yet, it does not. So we head inward, toward the galactic center, to meet the second barrier. The Magellanic story happens in the quiet outskirts, where danger arrives like wind and erosion. Now we jump to the opposite extreme, the crowded core of the Milky Way, where danger is not slow loss, it is sudden energy. This is the region where the galaxy should be loud, violent, and radioactive enough to make life feel like a reckless hobby. The center of the Milky Way is about 26,000 light-years from Earth. That number is easy to say and hard to feel. If you could ride a beam of light, it would still take you 26,000 years to arrive. You would leave now and reach the core long after every human language has either evolved into something unrecognizable or disappeared entirely. And the closer you get, the stranger the environment becomes. Stars are packed tighter. Gas clouds are denser. Everything moves faster. In the inner region, the night sky from any hypothetical planet would not be a gentle sprinkle of stars. It would be a crowd. Stars bright enough to cast shadows. Hundreds, maybe thousands of points brighter than anything we see from Earth, hanging close together like lanterns in a festival that never ends. Then right at the center sits the object that people love to mythologize, Sagittarius. A star is the name we give to the supermassive black hole at the Milky Way's heart. It has a mass of roughly 4 million suns, compressed into a region smaller than the orbit of Mercury. That is the part that always melts the brain. Millions of suns crammed into a space that would fit inside the inner solar system. Gravity there is not a gentle pull. It is a steep cliff. Stars near it race around at thousands of kilometers per second. Some complete orbits in just a few years. Our Sun, by comparison, takes about 230 million years to complete one slow lap around the galaxy. The center is not just a place, it is a different pace of reality. And yet Sagittarius' star is oddly quiet. Black holes have a reputation as cosmic vacuum cleaners, but that image is misleading. A black hole does not suck like a straw. It attracts by gravity like anything else with mass. The difference is how deep its gravity well is, and what happens to matter that gets too close. If gas falls in, it heats up, it swirls, it compresses, and in that process it can release enormous energy. But Sagittarius' star right now is not eating much. It is more like a giant predator dozing with one eye open. Occasionally it snacks. Occasionally a gas cloud wanders too close. Occasionally matter spirals inward and flares. But compared to the blazing active black holes we see in other galaxies, it is calm. So you might think the galactic center is safer than the movies suggest. That is where the second danger enters, and it does not care how hungry the black hole is, cosmic rays. The name is misleading because it sounds like light. Cosmic rays are not rays. They are particles, mostly protons, sometimes heavier nuclei, accelerated to extraordinary speeds. These are not the gentle protons drifting in the solar wind. These are bullets moving so fast that the phrase almost the speed of light is not drama, it is description. And when a particle moves that fast, speed becomes energy in a way we are not used to. A single proton is tiny. You could not see it with any microscope. But at extreme speed, one proton can carry the kinetic energy of something you can hold in your hand, like a hard-thrown ball. That sounds impossible until you remember that energy depends on speed, and near light speed the numbers get weird in a hurry. So what happens when those particles hit something? If they hit a human body, they can punch through cells and damage deoxyribonucleic acid, the molecule that stores biological instructions. That damage can cause mutations. If it hits electronics, it can flip bits in memory and cause glitches. If it hits a planet's atmosphere often enough, it can change the chemistry over time, weakening protective layers and increasing the amount of harsh ultraviolet that reaches the surface. This is not hypothetical. Even here on Earth, cosmic rays matter. Astronauts on the International Space Station receive higher radiation doses than people on the ground because the atmosphere below them is a thick shield. Satellites sometimes experience sudden faults because a charged particle slams into a component at the wrong moment. Engineers design space hardware with error correction and shielding specifically because of this invisible rain. Now imagine that rain turning into a storm. The inner galaxy should be one of the stormiest places, because cosmic rays are created by the same kind of violence that the galactic center specializes in. When gas falls towards Sagittarius A, it can form a hot swirling disk. That disk can heat matter to extreme temperatures. Shocks and magnetic fields can fling particles outward, and the center is full of massive stars that live fast and die young, exploding as supernovae on timescales much shorter than what we see in the calmer suburbs where we live. Supernova shock waves are one of nature's best particle accelerators. They are like giant moving walls of energy that can kick particles to insane speeds. Then add magnetic fields. Charged particles do not move freely through space like neutral dust. They respond to magnetic fields. They spiral around field lines. They bounce. They get trapped. The galactic center has strong magnetic fields, shaped and twisted by rotating gas clouds, stellar winds, and the restless environment around the black hole. Magnetic fields can both accelerate particles and confine them. So here is the setup for the paradox. The center of the galaxy should be generating cosmic rays constantly. Those cosmic rays should spread outward. Over time, you would expect a kind of diffusion, like smoke leaking from a fire. The inner region should slowly flood the surrounding parts of the galaxy with these high-energy particles, raising radiation levels across huge volumes of space, and if that flood was strong enough, it would matter for habitability. Planets closer to the center would face a harsher environment. Surface life would struggle on worlds without strong magnetic fields or thick atmospheres. Complex ecosystems would be harder to sustain. Civilizations would have to cope with higher failure rates in electronics and higher biological risk, unless they developed clever shielding or lived underground or underwater. So the galaxy should have a problem, a radiation leak from its core. For a long time, people assumed that leak was real and that the inner galaxy was simply a more punishing neighborhood. Not impossible, just harder. The universe is not required to make life easy. Then, in the early 2020s, scientists started noticing something that did not fit. When researchers studied gamma rays from the inner region, they were effectively studying cosmic rays indirectly. Gamma rays are produced when cosmic rays collide with gas. Map the gamma rays and you can infer where the cosmic rays are interacting. It is not a perfect method, but it is a powerful one, especially when you gather lots of data over time. And the data began to suggest something unsettling. The cosmic rays were not spreading out the way they should. Their density dropped faster with distance than simple diffusion predicted. The region looked less like a leaking fire and more like a contained system. Cosmic rays were being produced near the center, but they were not flooding the galaxy as expected. Something was blocking them, trapping them, or draining their energy before they could escape. In other words, there appeared to be a barrier, a containment system around the galactic center, a second shield, very different from the million-degree bubble around the Magellanic Clouds. This one was not about protecting gas from being stripped. This one was about protecting the wider galaxy from a storm of high-energy particles. And now the question becomes unavoidable. What could possibly hold back cosmic rays near the most chaotic region of the Milky Way? We are about to find out, and the answer is not a single lock on a door. It is more like 3 locks turning at once. A lot of astronomy feels like listening to a room through a wall. You cannot see the conversation directly, but you can hear muffled patterns and infer what must be happening inside. The cosmic ray barrier story is exactly that. Nobody pointed a camera at the galactic center and photographed a wall of particles. Instead, scientists noticed an absence, a missing flood. And in science, absence can be louder than presence. Cosmic rays are charged particles moving at extreme speed. When they collide with interstellar gas, they create secondary particles and high-energy light, including gamma rays. Gamma rays are the forensic residue of cosmic ray violence. So if you want to map where cosmic rays are interacting, one strategy is to map gamma ray emission. This is where the Fermi Gamma Ray Space Telescope enters the story. Fermi has been scanning the sky for years, collecting gamma ray photons the way a rain gauge collects water. Not dramatic bursts only, but a steady accumulation that lets you build statistical maps of where the galaxy is glowing at high energies. Around 2021, researchers digging into this data noticed something that made them pause. The distribution of cosmic rays in the inner region did not look like a simple diffusion problem. If the galactic center is producing cosmic rays and those particles are spreading outward, you would expect a relatively gradual fall-off with distance, like perfume dispersing through a room. Instead, the intensity appeared to drop too fast, too steep, like the smoke was hitting an invisible ceiling and pooling rather than spreading. That is the first clue, a gradient that is sharper than expected. Now this is the part where good scientists get suspicious of themselves first. Maybe the model is wrong. Maybe the gas distribution used in the analysis is inaccurate. Maybe background sources are contaminating the signal. Maybe instrument effects are being misread. The inner Milky Way is a messy region. There are many overlapping sources of gamma rays. Pulsars, supernova remnants, dense clouds, all of it layered along our line of sight. So the initial response is not celebration. It is paranoia in the healthy scientific sense. Double-check everything. But the pattern held. The best explanation was that cosmic rays were being confined or blocked from leaving the inner region efficiently. Not perfectly blocked, but enough to change the entire profile of how the particles were distributed. The researchers described it in terms that sound almost physical, like a boundary, a barrier, a containment zone. Not because they had found a literal wall, but because the math behaved as if the environment was acting like one. Now let us slow down and make sure we understand what is so weird about that. Cosmic rays are small. They are particles. They should move through space easily. They are not like gas clouds that can be trapped by gravity in neat orbits. A proton at near light speed should cross huge distances quickly. So why would a barrier even be possible? The answer is electromagnetism. Cosmic rays are charged. Charge means magnetic fields matter. And the inner Milky Way is laced with strong magnetic fields, shaped by the rotation of gas, the turbulence of stellar winds, and the extreme environment near Sagittarius A star. Magnetic fields do not need to be strong in the everyday sense to matter over large distances. A field that would feel weak in a laboratory can still steer charged particles across thousands of light years if the structure is coherent enough. And the inner region is not just magnetic, it is dense. Compared to the thin gas far out in the halo, the inner galaxy contains many regions of high-density gas, especially in the central molecular zone, a thick belt of cold, dense clouds orbiting the center. Dense gas is a target. When a fast particle plows into it, it collides, it loses energy, it creates gamma rays, and it becomes less of a long-range threat. So confinement does not have to mean a particle is trapped forever. It can mean the particle keeps colliding, losing energy, until it is no longer part of the dangerous high-energy population. That is why the barrier matters. Not because it creates perfect containment, but because it changes the balance between escape and loss. In other words, it turns a potential flood into a local storm. The Fermi data suggested that the galactic center was surrounded by a region where cosmic rays were being kept in, bounced around and drained. The researchers began calling it a cosmic ray barrier, and what makes that phrase so satisfying is that it describes a real effect without pretending we can see the underlying structure directly. It is a behavioral barrier, a physics barrier, a statistical barrier, but still a barrier. Now, because this is science and not mythology, there is no single satisfying villain or hero. The barrier is not one magical thing, it is likely a combination of mechanisms, each one contributing to the same outcome. But before we even get to those mechanisms, there is another reason this discovery hit so hard. It changes how you think about the inner Milky Way. We tend to imagine the galaxy as a disk where everything mixes eventually. Energy, matter, particles, it all circulates. The barrier implies the inner region can behave like a semi-closed zone, a place where cosmic rays are generated, but not freely shared with the rest of the disk. A place where the most intense radiation environment can be partly quarantined. That has consequences. If you're thinking about habitability, it suggests the inner galaxy might be less hostile than feared, at least in terms of runaway cosmic ray exposure. Not safe, but moderated. It suggests there is a built-in regulation mechanism, not designed for life, but with life-relevant consequences. If you are thinking about galaxy evolution, It suggests energetic particles can be stored and processed locally, changing heating, chemistry, and star formation in the inner region differently than if everything leaked outward. And if you are thinking about Sagittarius A star itself, it suggests the black hole is not just a passive object at the center. Its environment is actively shaping particle populations on scales of thousands of light years. Now let us not oversell it. Some cosmic rays do escape. The barrier is not a sealed jar, but the data indicates the escape is reduced enough to matter. Enough that the cosmic ray density beyond the central region is lower than it would be without containment. So the question becomes the obvious next step. What exactly is doing the containing? This is where the story gets fun, because the candidates are all plausible, and the best answer may be a conspiracy of physics. A wind that pushes back, magnetic fields that trap, dense gas that absorbs, 3 locks on one door. And once you see those locks, the barrier stops feeling surprising. It starts feeling like the natural outcome of a crowded, rotating, magnetized gas-rich core, a place where charged particles cannot simply fly straight out like arrows. They get bent, scattered, slowed, and in many cases, neutralized. We open those 3 locks next, one by one. When you hear the phrase cosmic ray barrier, it is tempting to imagine a single clean boundary, like a wall drawn with a ruler. The real Milky Way is messier. Nature almost never uses one mechanism when it can use 3, especially in a place as chaotic as the galactic center. So think of the barrier less like a wall and more like a fortress built by accident. Not designed, but assembled by physics. A place where multiple features overlap in the right way, and the overlap becomes protection. The researchers who first characterized the barrier laid out 3 main mechanisms that could explain it. What is fascinating is that none of them needs to be perfect because together they can produce the observed effect. The cosmic rays do not need to be stopped completely, they just need to be slowed, trapped, scattered, and drained enough that the flood never forms. Let us open the first lock. A wind from Sagittarius. A star. Even though Sagittarius A star is quiet compared to active black holes, it is not asleep. Gas does fall toward it, and when gas falls toward a black hole, it does not fall politely. It swirls, compresses, heats, and in many cases, it gets so hot that it cannot settle. Instead of crossing the point of no return, much of it can be blown outward as a hot outflow. This is a black hole wind. Not like a breeze you would feel, but a flow of hot plasma moving outward at thousands of kilometers per second. Now imagine you are a high-energy charged particle trying to leave the region. If you're moving outward, you are moving into an oncoming wind or sideways through a turbulent outflow. You collide with particles in that hot gas. You lose energy, you scatter, you get deflected. It is like trying to run through a crowd that is moving against you. You might still escape, but your progress is slowed and many particles will be trapped long enough to lose their bite. The wind does not need to physically grab a cosmic ray. It just needs to increase the chance that the ray interacts with something before it reaches open space. So the wind acts like a pressure zone, a region where outward travel is resisted. That is lock 1, a moving medium that pushes back. Now lock 2, magnetic fields. This is the most elegant lock because it does not require dense gas. It uses the fact that cosmic rays are charged. Charged particles do not fly like bullets through a vacuum. In a magnetic field, they curve, they spiral, they follow the field lines, and if the field lines are tangled, the particles take tangled paths. The galactic center has magnetic fields that are much stronger than what we experience in the solar neighborhood. Not stronger than a fridge magnet, but stronger on a cosmic scale, and structured by constant motion. Gas clouds rotate around the center. Stellar winds blow. Supernova shocks pass through. The magnetic field gets stretched, twisted, and braided. So picture an invisible labyrinth. Not walls of stone, but corridors defined by magnetic lines. A cosmic ray tries to leave, but its path bends. It follows a loop, then another. It gets reflected by irregularities. It is not moving in a straight line outward anymore. It is bouncing around like a pinball in a machine, covering lots of distance without making much progress away from the center. This is important because confinement does not mean the particle is frozen. It means the particle's escape time becomes long. The longer it stays, the more likely it is to collide with gas and lose energy. The magnetic labyrinth and the wind work together. The wind provides collisions. The magnetic field provides wandering. That is lock 2, a trap made of geometry. Now lock 3, a dense ring of gas. About 1,500 light-years from the centre is a region called the Central Molecular Zone. It is essentially a thick belt of dense gas clouds rotating around the core. It contains millions of suns worth of gas. It is the raw material for future star formation in the inner galaxy, and it is dense enough to matter for cosmic rays. A high-energy particle passing through dense gas does not glide through untouched. It collides, it loses energy, it creates secondary particles, it generates gamma rays. In some cases, it transforms into a less energetic particle population that is no longer a long-range danger. So the dense ring acts like a barrier in a different sense. Not a wall that reflects, but a wall that absorbs and grinds down energy. If you want an analogy, imagine sandpaper wrapped in a ring. The particle can try to cross it, but the act of crossing takes energy away. Many particles will not emerge with the same dangerous speed they had before. The ring turns sharp into dull. Now stack these 3 locks together. The wind creates a hostile outflow environment. The magnetic fields keep the particles wandering in circles. The dense ring absorbs and drains energy from those that try to push through. The combined effect is that cosmic rays produced near the centre build up locally into what some researchers call a sea, a population of particles trapped in the inner region, rather than a flood spreading outward across the galaxy. This is why the barrier can appear in data even if no single mechanism is perfect. The galaxy does not need one perfect solution. It has 3 decent ones working at once. And there is another twist that makes this feel less like a static feature and more like a living system. The barrier changes over time, because the wind strength depends on what Sagittarius A star is doing. When the black hole is feeding more actively, it can drive stronger outflows. Those outflows can intensify the barrier. When the black hole is quieter, the wind weakens, and more cosmic rays may leak outward. Not a total collapse, but a change in permeability. The centre, in other words, has breathing defences. We even have clues that Sagittarius A star was more active in the past. One of the most dramatic pieces of evidence is a pair of enormous gamma-ray structures extending above and below the galactic plane called the Fermi bubbles. Each extends tens of thousands of light-years. They are like 2 giant lobes of high-energy emission emerging from the centre, suggesting that millions of years ago, the black hole had an energetic episode that pumped huge amounts of energy into the surrounding environment. If the centre can do that, then the barrier is not just a passive consequence. It is part of a cycle. Activity produces outflow. Outflow shapes cosmic ray containment. Containment shapes where energy is deposited. Energy deposition shapes the environment the black hole is feeding from. Feedback again, and feedback is the theme of this entire story. The Magellanic corona is self-maintained by motion. The cosmic ray barrier is shaped by winds, magnetism, and dense gas, and those features respond to the activity they help regulate. So now we can answer the question that haunted the previous part. Why does the Milky Way not drown in cosmic rays from its centre? Because the centre is not an open faucet. It is a region with built-in traps, and the traps slow the escape long enough for many particles to lose their energy locally. That is shield number 2, and it matters for habitability in a way that is easy to miss. Without that barrier, the inner galaxy would be far more punishing. Worlds closer to the centre would face far higher radiation exposure. Life would be forced into deeper refuges. Complex ecosystems under open skies would be much less likely. The barrier does not make the inner galaxy friendly, it makes it less insane. In the next part, we do something that always feels a bit dangerous but also clarifying. We imagine the barrier failing, not because it will, but because imagining the failure reveals what the barrier is doing every day. And we map what it means for the kinds of worlds that can exist inside a galaxy with a self-regulating core. When people talk about the Milky Way being dangerous, they usually mean the obvious villains. Supernova explosion, gamma-ray bursts, rogue asteroids, black holes. The cosmic ray barrier forces a subtler thought. A galaxy can be dangerous without dramatic events, simply by leaking the wrong kind of particles into the wrong regions for long enough. Cosmic rays are slow disasters. They do not need to arrive in one catastrophic wave. They can change a planet by constant bombardment over millions of years. nudging chemistry, damaging biology, and stressing atmospheres until the environment becomes hostile. So if the galactic center really produced a large, steady outflow of the most energetic particles, it would not need to sterilize worlds overnight to matter. It would matter by raising the background radiation of the inner galaxy for eons. That is why the barrier is such a big deal. It is not a Hollywood shield, but it is a moderator of long-term conditions. To feel what it does, imagine the inner Milky Way without it. Start near the center, within a few thousand light years. In that region, star density is high. Massive stars are more common. Supernovae are more frequent. Magnetic fields are stronger. Gas clouds are dense and turbulent. It is already a rough neighborhood. Now add a free-flowing flood of cosmic rays from Sagittarius A star's environment, spreading outward with far fewer obstacles. What changes first? Radiation levels rise, charged particles slam into planetary atmospheres and create cascades of secondary particles. Some of those particles reach the surface, some break apart molecules in the upper atmosphere. Ozone-like layers, if present, can be weakened. Biological mutation rates rise. Electronics, if any exist, have a much harder time. Satellites become unreliable. Communication systems become noisy. For any technological civilization, the sky becomes a constant hazard. Now think about planets. A planet can defend itself in two main ways. A thick atmosphere can absorb incoming particles. A strong magnetic field can deflect many charged particles away from the surface by forcing them to spiral along field lines. Earth has both. That is why cosmic rays are mostly an annoyance for satellites and astronauts, not a daily existential crisis for surface life. But many planets will not have both. A world with a thin atmosphere like Mars has less shielding. A world without a strong magnetic field has little abilities to deflect charged particles before they start tearing into the upper atmosphere. Over long timescales, the atmosphere itself can erode, especially if the particle flux is high. A planet can slowly bleed air into space. Now, take a planet in the inner galaxy closer to the source and raise cosmic ray intensity by orders of magnitude. A planet like Earth might still protect surface life, but it would be stressed. A planet with weaker defenses could become uninhabitable at the surface, forced into underground refuges or deep oceans where water and rock provide shielding. You would not see forests under open sky, you would not see wide grasslands and animals thriving in sunlight. The surface becomes a harsh zone, a place life avoids unless it involves extreme protection and rapid repair. And that is only the biological angle. There is also the atmospheric chemistry angle. Cosmic rays can create nitrogen oxides and other reactive species that alter climate and protective layers. They can change cloud formation and influence greenhouse balance indirectly, not in a simple one-to-one way, but as a persistent pressure on the system. So the inner Milky Way without containment would be a tougher place to build and sustain complex ecosystems. Now bring the barrier back. The barrier does not remove cosmic rays from the center, it changes where their energy goes. It keeps many high-energy particles trapped long enough that they collide with dense gas, lose energy, and produce gamma rays locally. That means the danger is concentrated. The inner region becomes brighter in high-energy light, but the wider disk receives a reduced share of the most damaging particles. In other words, the barrier quarantines. This does not mean the rest of the galaxy is safe. Cosmic rays still exist everywhere. Supernovae still launch particles, and some particles do leak from the center. But the difference between a trickle and a flood matters over millions of years. It also means the inner galaxy might not be as uniformly hostile as we once assumed. You can imagine zones. Closest to the center, it is still harsh. The density of massive stars, the frequency of energetic events, and the overall turbulence make it challenging for stable long-term conditions. But farther out, inside the region that would have been overwhelmed by a free-flowing flood, the barrier may lower the radiation background enough that planets with decent shielding could maintain surface life more easily. We should be careful here. We do not have a full habitability map of the Milky Way. We do not even know how common Earth-like planets are in the inner bulge compared to the disk. We do not know how often planets there have strong magnetic fields. We do not know how life responds to long-term radiation environments different from Earth's. But what we can say is simple. The barrier changes the rules. It makes the inner Milky Way less of a cosmic firing range than it would be otherwise. It increases the chance that some worlds closer to the center could have stable atmospheres and long evolutionary timelines, rather than being constantly reset by particle storms. Now place Earth in this picture, because it is tempting to assume we are far away from all this. We are about 26,000 light years from the galactic centre. That puts us outside the densest inner region. We are not in the worst possible radiation environment, but we are also not absurdly far. If the barrier were dramatically weaker, we might detect a change in cosmic ray intensity over long time spans. Not a sudden apocalypse, but a measurable shift, like a background hum getting slightly louder. From our perspective, the cosmic ray barrier is a distant feature. From the perspective of billions of stars inside the inner galaxy, it is an environmental regulator. And that returns us to the larger theme. These shields are not designed for life, but they shape the conditions that make life possible. The Magellanic Corona buys time for dwarf galaxies to keep forming stars. The cosmic ray barrier buys stability for regions of the inner Milky Way to avoid being saturated by the most energetic particles. Now we move to the third shield, the strangest one in a different way. Because it is not a bubble you can map with X-rays, it is not a barrier you can infer from gamma rays. It is a filter at the edge of our galaxy revealed by patterns in the rarest particles we detect on Earth. To understand that edge, we have to meet a telescope that is not a telescope. A normal telescope collects light. It gathers photons, sorts them by colour, and turns faint signals into images. But the third shield is not mainly revealed by light. It is hinted at by something stranger and rarer. Particles so energetic that when one hits Earth's atmosphere, the impact is not a flash. It is a cascade. That is why one of the key instruments in this story looks nothing like a telescope. In Argentina, spread across about 3,000 square kilometers of grassland, sits the Pierre Auger Observatory. It is a giant net designed to catch the rarest rain in astrophysics, ultra-high energy cosmic rays. These particles are so uncommon that you might expect about one event per square kilometer per century at the very highest energies. If you want enough data to do real science, you cannot build one detector, you build a landscape. The observatory uses about 1,500 water tanks arranged in a wide grid. Each tank holds many tons of purified water and sensitive detectors. When a cosmic ray slams into the upper atmosphere, it triggers a shower of secondary particles. That shower spreads out as it falls. Some of those particles reach the ground. When they pass through the water in the tanks, they produce faint flashes of light that the detectors can register. So the Pierre Auger Observatory does not see the original particle directly. It sees the footprint the particle leaves across the ground. Which tanks triggered, in what order, with what intensity. From that pattern, scientists reconstruct the incoming direction and estimate the energy, like detectives rebuilding a crime scene from scattered evidence. It is hard to overstate how weird this is. We are trying to learn about the edge of our galaxy using particles that were born in violence far away, travelled for millions of years through interstellar and intergalactic space, then died in our atmosphere, leaving only a brief shower of debris. And yet, with enough events, you can build maps, statistical maps, not photographs, but maps that reveal structure. This is where the galactic edge enters the story. When you picture a galaxy, you probably imagine a sharp border, like an island surrounded by empty ocean. The Milky Way is not like that. The bright disk of stars does have a recognizable extent, but the galaxy fades outward into a halo. Gas thins, star density drops, magnetic fields weaken and change shape, dark matter dominates the mass budget more and more. The Milky Way becomes less like a city wall and more like a long twilight zone. That twilight zone is the boundary between being inside a galaxy and being out in intergalactic space. And boundaries matter, because the environment changes the rules of travel. Cosmic rays are charged particles, which means magnetic fields influence them. Even weak magnetic fields can bend their paths over long distances, especially if the field structure is coherent. The Milky Way has a magnetic field that extends far beyond the visible disk. It is not a neat bar magnet. It is tangled, looped, and shaped by the galaxy's rotation and the motion of plasma. So when ultra-high energy cosmic rays arrive from outside the Milky Way, they do not necessarily fly straight in like arrows. Some are deflected, some are delayed. Some might even be temporarily trapped in boundary regions, depending on their energy and their composition. In other words, the edge can behave like a filter. Not a solid wall, not an impenetrable shield, but a region where incoming particles get sorted. Some make it through, some arrive from slightly different directions than they would have without the field. Some lose energy through interactions with gas and plasma. The galaxy's outskirts can shape what enters and how it enters, and that shaping leaves fingerprints in the data. When scientists map the arrival directions of the highest energy cosmic rays, the distribution is not perfectly random. There are preferences, subtle anisotropies, patterns that suggest we are not just detecting a uniform drizzle from all directions. Some parts of the sky contribute more events than others. Some energy ranges show features that look like a transition between populations inside the galaxy versus outside it. Now, we have to be careful. Cosmic ray astronomy is complicated. Magnetic fields between galaxies also exist, though they are weak and poorly mapped. Sources themselves are not uniformly distributed. Active galaxies, clusters, and cosmic structure can create real directional biases, and our detectors have their own limitations. But even after accounting for those factors, there are hints that the Milky Way's boundary region is doing something non-trivial. So what could the edge filter actually be? Researchers discuss several possibilities, and the frustrating truth is that more than one could be contributing at once. One possibility is that the magnetic fields at the boundary are stronger or more organized than we think. Most of our magnetic field measurements are better in regions closer to us and closer to the bright disk, because we have more tracers there. The outer halo is harder. But if the field lines compress, align, or form boundary layers where galactic plasma meets intergalactic plasma, you could get a region that bends incoming trajectories more effectively than simple models predict. Another possibility is that the transition region has plasma behavior we have not fully captured. When you have sharp gradients in density, temperature, and magnetic structure, you can get instabilities. Waves, turbulence, scattering. A particle passing through a messy boundary is like a swimmer crossing surf. Even if the ocean is open, the shoreline changes the motion. A third possibility is more speculative, but it keeps showing up because the edge is where dark matter dominates. The Milky Way is surrounded by a halo of dark matter extending far beyond the visible stars. We know it is there because of gravity, but we do not know what it is made of. If dark matter has even rare interactions with normal matter, or with cosmic rays beyond pure gravity, the cumulative effect across huge distances could leave subtle signatures in direction and energy distributions. This idea is not confirmed. It is an invitation, not a conclusion. But it highlights why the edge is such a tempting laboratory. It is one of the few places where ordinary matter thins out and the invisible mass becomes the main actor. There is also a fourth possibility that sounds boring but is often true. It is a combination. Magnetic fields deflect some particles. Boundary turbulence scatters others. The source distribution shapes what arrives in the first place, and the result is a pattern that no single effect explains cleanly. But together they produce the filtering behavior we infer. This is frontier science in the honest sense. We are using rare messengers to probe an environment we cannot visit, and we are trying to decode a signal that has been bent and blurred by everything it passed through. But here is why it matters. The edge of the Milky Way defines what enters our galaxy and what escapes it. If the boundary filters incoming cosmic rays, it changes how energy is deposited into the halo. If it affects outflowing particles from inside the galaxy, it changes how the Milky Way loses energy and matter to intergalactic space. Over billions of years, those flows influence how galaxies evolve. So the third shield is not just a defensive border, it is a regulator of exchange. It mediates the conversation between our galaxy and the wider universe. And now we have three shields in view, each one revealed in a different way. A hot corona protecting neighbor galaxies from being stripped too quickly. A cosmic ray barrier keeping the galactic center from leaking a harsh particle storm into the disk. And a boundary filter that shapes what enters and what leaves at the edge. The obvious next move is to do something dramatic. To imagine what would happen if all three suddenly vanished. Not because that will happen, but because the thought experiment forces us to see what they're doing every day. Quietly, constantly, for billions of years. We run that experiment next. Imagine you wake up tomorrow and nothing looks different. The stars are still there. The Milky Way still arches overhead. The galaxy seems calm. But in the invisible layers, three quiet regulators are gone. The Magellanic corona is no longer cushioning the clouds. The inner barrier is no longer holding back the highest energy particles. The edge no longer filters what arrives from the wider universe. The Milky Way has not exploded. It has simply stopped managing its own extremes. And that is how the trouble begins. Start in the outskirts with the Magellanic Clouds. Without their hot envelope, the interaction becomes direct and brutal. 400 kilometers per second through the Milky Way halo is no longer a manageable headwind. It becomes a stripping knife. Gas that used to be protected in the inner regions is suddenly exposed. Star-forming clouds are peeled away faster than they can collapse. Over a few million years, the brightest stellar nurseries begin to dim. Not because stars vanish, but because the factory that makes new stars is being shut down. On the scale of 10 million years, which is nothing in galactic time, the Large Magellanic Cloud loses a huge fraction of its remaining star-forming fuel. The Small Magellanic Cloud, with less gravity to hold on, fares worse. By the time 100 million years pass, both galaxies still contain their old stars, but they feel like different objects. Their young blue populations thin out, their brightest regions go dark. If any civilization lived there, they would not need a telescope to know something is wrong. Their galaxy would be aging in fast forward. The Magellanic Stream reacts like a wound that suddenly opens. What used to be a slow leak becomes a flood. The ribbon thickens, more gas is dumped into the wake in a shorter time. Over tens of millions of years, the stream becomes heavier, brighter in radio maps, more chaotic, more clumpy. The Milky Way does not just receive that gas gently, it gets slammed with it. That has consequences for our own galaxy's outer disk. Gas arriving in large clumps can trigger bursts of star formation, short violent episodes where massive stars form quickly and then die quickly. Those massive stars explode as supernovae, heating surrounding gas and disrupting the calm rhythm of the spiral arms. Instead of a steady long burn, parts of the outer Milky Way begin to flicker, bright knots here, exhausted gaps there, a spiral pattern that looks less elegant and more scarred. Now shift your attention inward, to the galactic center. When the cosmic ray barrier collapses, the particles that were trapped and wandering in that inner region begin to escape more freely. Cosmic rays move near the speed of light, so the information of the collapse spreads quickly. Within a few thousand years, the inner galaxy sees a dramatic rise in the flux of high-energy particles. Worlds that were already stressed become far more stressed. Atmospheres are hammered, chemistry is pushed, radiation levels climb. The most severe effects land close to the center. Planets within a few thousand light-years that do not have strong magnetic shielding and thick atmospheres begin to lose the battle over long spans of time. Surface life becomes harder to sustain. Complex ecosystems become rarer. The inner Milky Way starts to behave more like the harsh version we used to imagine, a region where life would need deep refuges and extreme repair. Farther out, the wave is diluted, but it still matters. If you are a scientist on a planet like Earth, you notice the numbers shift. The rate of particle hits in the upper atmosphere creeps upward. Not an instant catastrophe, but a measurable increase that echoes through long time spans. The galaxy's core becomes a brighter gamma ray source from the outside, because cosmic rays escaping and colliding with gas light up larger regions. To distant observers in other galaxies, the Milky Way looks like it developed a radiation leak. And then comes the strangest consequence, because it happens at the boundary where our galaxy meets the space between galaxies. When the edge filter stops doing whatever it is doing, the highest energy particles from beyond the Milky Way arrive less moderated. These extragalactic cosmic rays include not just protons, but heavier nuclei accelerated by extreme events in distant galaxies. Their arrival does not destroy the Milky Way, it changes the halo. The outer halo is a vast volume of thin gas. When ultra-energetic particles plow through it, they deposit energy. The effect is heating, not a dramatic flare you can watch with your eyes, but a persistent input that raises the temperature and pressure of the halo gas. Pressure wants to expand. Over tens to hundreds of millions of years, the halo becomes puffier. The galaxy's outer gas distribution loosens. Some fraction of gas reaches speeds that allow it to drift away, which means the Milky Way begins to lose a little mass to intergalactic space. Little matters when you multiply it by a billion years. As the halo expands and the outer regions grow more diffuse, the sharpness of the galaxy's outer boundary fades. The spiral arms become less distinct, not because the stars instantly move, but because the long-term balance between gravity and rotation is being nudged. The Milky Way does not stop being a spiral. It becomes a softer spiral, a looser spiral, a galaxy that looks older than it should for its age. Now stack all three failures together and you get a cascade. The Milky Way loses its steady satellite supply line and replaces it with a messy gulp. The inner galaxy becomes more irradiated and more hostile. The outer halo becomes warmer, puffier and slightly leakier. Over 1 billion years, those changes compound into a Milky Way that is less stable, less organized, and less efficient at doing the slow work galaxies are built for, which is forming stars at a sustainable pace for a very long time. Here is the part that matters, and it is the reason this thought experiment is useful. Nothing in that scenario requires magic. It is all just physics responding to the removal of regulators. When the regulators exist, they do not stop change, they shape the tempo of change. They turn sudden into gradual, they turn floods into trickles, they turn chaos into something a galaxy can live with. And that is why calling them shields is not just a metaphor. A shield is not about invincibility, it is about survivable conditions. In the next part, we step back from the nightmare version and ask the obvious question you are probably thinking right now. If these shields matter so much, why would they ever disappear? What makes them stable for billions of years? What makes them feel less like fragile mechanisms and more like consequences of the galaxy being what it is? The thought experiment is terrifying because it feels plausible. Remove the shields and the Milky Way slowly unravels into a harsher, messier version of itself. But after the fear comes the relief, because there is a reason the experiment stays in your imagination. These shields are not machines. They are not devices with parts that corrode. They are not delicate constructions waiting for a screw to fall out. They are patterns that appear when you combine gravity, motion, gas, and magnetism in a rotating galaxy. They are not optional features bolted onto the Milky Way. They are what the Milky Way looks like when physics has had billions of years to settle into its habits. Start with the Magellanic corona. The reason it persists is the same reason it was born. The clouds are moving through the Milky Way halo. That motion creates pressure on the leading edge. Pressure compresses gas. Compression heats gas. Hot gas becomes a low-density buffer. As long as the motion continues, the heating continues. As long as the heating continues, the buffer is constantly renewed. So the corona is not a bubble that formed once and then just drifted there like a ghost. It is a process, a standing wave of sorts, a shape maintained by ongoing flow. If the environment changes, the shape changes. If the halo gets denser in one region, the front compresses more. If the clouds move through a thinner region, the compression weakens and the corona thins. But the basic mechanism does not stop. It is the same way a bow wave sits in front of a moving ship. The wave is not stored water. It is water responding continuously to motion. That is why the corona can buy billions of years. Not because it is invulnerable, but because it is constantly rebuilt by the very threat it blunts. Now look at the second shield, the cosmic ray barrier. Here the stability comes from redundancy. 3 locks, not one, a wind, a magnetic maze, and a dense ring of gas. The wind depends on gas falling towards Sagittarius A star. That supply is not steady, but it is persistent. The galactic center is full of gas clouds, stellar winds, and turbulence. Some gas drifts inward, some gets heated, some gets blown outward again. Even when the black hole is quiet, the environment is not still. The wind can weaken or strengthen, but the cycle does not vanish unless the center somehow becomes empty of gas, which is not something that happens suddenly in a galaxy. The magnetic fields are even more stubborn. A rotating, conducting plasma naturally generates and maintains magnetic fields through processes that are messy but persistent. The Milky Way rotates, gas moves, turbulence stirs, field lines get stretched and twisted. You do not need a designer to keep them on. You need motion, and galaxies are basically motion with scenery. Then there is the dense ring, the central molecular zone. That structure is held in place by gravity and by the same orbital dynamics that keep gas circulating in the inner galaxy. It can change shape, form stars, get disrupted in parts, but it does not simply disappear overnight. It is a reservoir, and reservoirs take time to drain. So even if one lock becomes less effective at some moment, the other locks still matter. The barrier is not a single fragile gate. It is a whole neighborhood that happens to be good at trapping and draining charged particles. And the most important point is this. Cosmic rays are not a special substance the galaxy must remember to contain. They are charged particles. Charged particles always interact with magnetic fields. They always scatter in dense gas. If the inner Milky Way is magnetized and gas-rich, then containment is not an extra feature. It is a consequence. Now the third shield, the edge filter, is the least understood, which makes it feel the most mysterious and therefore the most fragile. But the opposite may be true. The boundary between a galaxy and intergalactic space is not a wall you can knock down. It is a transition zone created by the galaxy's extended halo, its magnetic environment, its outflows, and its dark matter scaffold. Those things exist on enormous scales and change slowly. You cannot flip a switch and remove a dark matter halo. You cannot quickly erase a magnetic field that is being regenerated by ongoing rotation. You cannot instantly smooth out the boundary between two different cosmic environments. So even if the exact filtering mechanism turns out to be more complex than we currently imagine, the fact that there is a transition region at all is unavoidable. Where conditions change sharply, behavior changes sharply, filters emerge. That is why the shields do not feel like inventions, they feel like equilibrium. Now, none of this means the Milky Way is frozen. These systems evolve over billions of years. The Magellanic Clouds will lose gas and eventually merge or dissolve into the Milky Way. Over millions of years, Sagittarius A will go through quieter and more active phases, and the cosmic ray barrier will breathe with those changes. Over cosmic time, the Milky Way's outer halo will respond to accretion, to outflows, to interactions with other galaxies. The shields persist, but they adapt. That idea is strangely comforting. It means the galaxy is not held together by luck alone. It is held together by feedback. When something pushes too hard, other processes respond. When energy builds up, it finds channels. When motion creates danger, motion also creates buffers. And it also means our view of the Milky Way has been incomplete for most of human history for a simple reason. These systems are not bright, invisible light. We evolved eyes for a narrow band of wavelengths that were useful on a planet under a sun. The galaxy does much of its most important work in regimes we cannot see without technology, which leads to the next turning point in the story. For all the talk of shields, most of what we know has come from indirect traces, ultraviolet hints, X-ray glows, gamma-ray maps, statistical patterns in particle arrivals. We have been listening through walls, but we are entering an era where the walls get thinner. New instruments are coming online that can map hot gas with far better precision, trace gamma rays with sharper detail, and measure cosmic rays with better composition and direction. We are not going to see these shields with our eyes, but we are going to see them with something that counts just as much in science. Resolution. We are about to watch the invisible become measurable in a way it never has before. Up to now, this story has been a triumph of the inference. We see a stream and deduce a shield. We see gamma rays and deduce a barrier. We see statistical patterns in rare particles and deduce a filter. It works, but it also leaves that lingering feeling of, are we sure? Astronomy lives with that feeling because you cannot pick up a galaxy and weigh it in your hand. You have to interrogate it from afar. But the next phase of this research is different. The question is no longer only, do these shields exist? The question becomes, what do they look like in detail? How do they change, and how do the pieces interact? That requires better vision, and not in the visible sense. It requires instruments that can measure hot gas precisely, map gamma rays sharply, and catch more of the rarest cosmic rays with less uncertainty. Start with the Magellanic Corona. Detecting it was hard because it is enormous and faint. Measuring it in detail is harder because you need spectroscopy, the ability to break high-energy light into its precise energies. Spectroscopy is like turning a glow into a fingerprint. Different elements and different temperatures produce different signatures. If you can measure those signatures accurately, you can map temperature, density, and composition across the corona, instead of just saying it is there. This is why high-resolution X-ray spectroscopy matters. It is the difference between knowing a weather system exists and knowing its wind speed, humidity, and temperature gradients. Once you can map those gradients, the corona stops being a single blob and becomes a dynamic structure. You can ask where it is thickest, where it is failing, where it is mixing with cooler gas, where turbulence is shredding it, and how it responds as the clouds move through regions of different halo density. That detail is not just satisfying, it is decisive. If the corona's composition matches the clouds, that strongly supports the idea that the shield is built from their own gas. If the composition is different, then the story becomes stranger, implying a larger exchange with the Milky Way halo than we assumed. Now the cosmic ray barrier. Here, gamma ray mapping is the main tool, because gamma rays are produced where cosmic rays collide with gas. Better gamma ray maps mean better cosmic ray maps, and better maps let you distinguish between the three locks. If a wind is doing most of the work, you might expect a certain spatial structure, perhaps an outflow-shaped gradient. If tangled magnetic fields dominate, you might see confinement patterns that correlate with magnetic structures traced at radio wavelengths. If the dense ring is the main absorber, you would expect a boundary linked to the central molecular zone. To untangle those possibilities, researchers need sensitivity and angular resolution. Sensitivity tells you how faint a signal you can detect. Angular resolution tells you how fine the detail is on the sky. The next generation of gamma-ray observatories and ground-based arrays are designed to improve both. When you can resolve structure on the scale of a few light-years instead of hundreds, the barrier stops being a concept and becomes geography. It also becomes time-dependent science. If Sagittarius A has even modest variability, if a gas cloud falls in and creates a flare, if a supernova explodes in the inner region, then cosmic ray populations change. The barrier should respond. It should strengthen in places, weaken in others, shift boundaries, change leakage channels. Those are not changes you can watch in a single night. But across years of monitoring, you can start to see the center breathing. Now the edge filter. This is the hardest one because the edge is far and the particles are rare. Progress here depends on two things: more events and better reconstruction. More events means bigger detectors, longer observation times, and new ways to detect showers. Better reconstruction means improved electronics, improved models, and crucially, composition measurement, knowing what kind of nucleus caused the shower. Composition is key because different mechanisms affect different particles differently. A magnetic filter does not treat heavy nuclei the same way it treats protons. A turbulent boundary might scatter some energies more than others. If dark matter interactions exist, they might have signatures that depend on energy or particle type. If you can sort incoming cosmic rays by composition and energy with better accuracy, you gain a new axis of information. The patterns become less ambiguous. You can start ruling out explanations instead of just collecting them. This is where upgrades to existing observatories matter. More detectors increase the catch. Better timing improves directional accuracy. New detectors that measure shower development more precisely improve composition estimates. Every incremental upgrade turns the edge from a fuzzy question into a constrained problem. There is also a deeper shift happening in astronomy that makes all of this more powerful: coordination. For much of the last century, instruments operated like isolated detectives. One team looks in radio, another in X-rays, another in gamma rays, another counts particles. They publish in parallel and later someone tries to stitch the stories together. Now the trend is toward multi-messenger campaigns. Coordinated observations across many wavelengths and particle channels at the same time. The reason is simple. If you observe the same region simultaneously, you know you are seeing the same state. You remove a major uncertainty, which is time. This approach has already proven itself dramatically in other areas, like events involving neutron stars where gravitational waves and electromagnetic lights together revealed a full story neither could tell alone. The same idea applies here. X-rays trace hot gas, ultraviolet traces warm transition zones, radio traces magnetic fields, gamma rays trace cosmic ray interactions. Cosmic ray detectors trace the highest energy particles directly. Combine them, you can build something like a three-dimensional model of the shields. Not a perfect map, but a coherent one. A model where the corona's shape, the barrier's boundary, and the edge, filter's effects are all part of one system. That last phrase matters, because once you have three shields, the most tempting question is whether they are truly independent. Does the cosmic ray barrier influence particle populations that later encounter the edge filter? Do outflows from the center feed the halo in ways that change boundary conditions? Does the Magellanic interaction stir the outer halo and magnetic environment in ways that subtly affect cosmic ray paths? Those are not wild ideas. They are exactly the kinds of couplings that appear in complex systems. The Milky Way is not a set of isolated compartments. It is one rotating plasma structure with nested environments. So the future of this research is not only sharper pictures, it is systems thinking. Seeing the Milky Way less like a static spiral and more like an ecosystem with feedback loops, flows, and regulators. Now, before we end the story, there is one more layer we need to address. The human layer. The meaning layer. Not in a sentimental way, but in a reality check way. Because the final twist is that these shields are not protecting us specifically. They are not a cosmic security system tuned to humans. They are in different patterns. But by being indifferent and stable, they have shaped the possibility space in which planets and life can exist. And that is where we close. There is a trap we fall into when we learn about something protective in nature. We start talking as if the universe built it for us, as if the galaxy cares, as if there is intention hidden in the structure. There is no evidence for that. The Milky Way does not know you exist. The Magellanic Corona is not hovering around those dwarf galaxies out of kindness. The cosmic ray barrier is not standing guard so life can flourish. The edge filter is not a customs agency carefully inspecting incoming particles for the safety of developing civilizations. These are not plans, they are consequences. But here is the strange thing. Consequences can look like design when you live inside them. A rotating galaxy filled with gas and magnetic fields naturally produces buffers, traps, and transition layers. Hot gas forms envelopes when motion compresses and heats it. Charged particles get confined when magnetic fields and dense gas are arranged in the right way. Boundaries filter flows when environments change sharply. None of this requires a purpose, it requires only that physics runs consistently. And that consistency is the real story. Because the universe is violent, there is no point pretending it is not. Stars explode, black holes flare, radiation fills space, particles slam into atmospheres. Galaxies tear at each other through gravity and tides. Over cosmic time, destruction is common, but the universe is also structured. The same laws that allow violence also allow stability. They allow matter to settle into long-lived patterns. Galaxies persist for billions of years. Stars like the Sun shine steadily for billions. Planets can orbit in stable paths. Chemistry can run long enough to build complexity. Evolution can explore possibilities for enormous spans of time. The shields are part of that stability story. They are not miraculous, they are mundane in the best way. They are physics doing what physics does, and the result just happens to be the moderation of extremes. Think about the Magellanic Corona again. It is a buffer born from motion. That is a feedback loop. The threat creates the defense slows the threat. The system becomes self-regulating over time. Think about the cosmic ray barrier. It is not one mechanism. It is redundancy. Wind, magnetism, dense gas. The center is not sealed, but it is regulated. The highest energy particles do not get a free highway into the disk. They get tangled, scattered, and drained. Think about the edge filter. It is the galaxy's handshake with the wider universe. Not a hard stop, but a region where conditions shift and therefore behavior shifts. The Milky Way is not an island with a coastline. It is an atmosphere fading into a larger atmosphere, and that layered structure shapes what comes in and what goes out. Now, place yourself in that picture without the old human reflex of making it about you. You are made of the galaxy, literally. Hydrogen in your body traces back to the earliest minutes after the Big Bang. Carbon in your cells was forged in stars. Oxygen was forged in stars. Iron in your blood was forged in violent stellar deaths. Those atoms drifted through interstellar space, mixed into clouds, collapsed into new stars, and eventually became part of a planet. Then chemistry ran on that planet long enough to build biology. Biology ran long enough to build minds. And now those minds can look outward and discover the invisible systems that help the galaxy stay stable long enough for any of this to happen. No one scheduled that outcome. It is not destiny. It is what can happen when the universe is both lawful and patient, and that is the real emotional punch of the shields. They remind you that stability does not require intention, it requires conditions plus time. The Milky Way has had about 13 billion years of time. That number is so large it becomes abstract, so let it land in a different way. These shields were operating before Earth existed, before the Sun existed. They were shaping the galaxy when the universe itself was young, and they will keep shaping it long after humanity is gone. That is not depressing. It is humbling. It means we are not the main characters of the galaxy. We are a temporary pattern inside a larger pattern. But it is also strangely comforting, because it means the galaxy's stability is not fragile in the way a human structure is fragile. It is not held together by maintenance crews. It is held together by physical laws that have been consistent since the beginning. As long as gravity remains gravity and electromagnetism remains electromagnetism, the basic tendencies that create these shields will continue. The Magellanic Clouds may eventually lose their gas and merge, but coronas like theirs will form around other satellites. The cosmic ray barrier may breathe with the black hole's feeding cycles, but the ingredients that to create containment will persist. The edge filter may turn out to involve mechanisms we have not yet pinned down, but the existence of a boundary layer is unavoidable in a galaxy with an extended halo. So the Milky Way is not just a collection of stars, it is a system, an ecosystem of plasma, gravity and magnetic fields, with flows of gas and energy constantly reshaping it. The shields are not exceptions, they are expressions of that system, and that is why learning about them changes your relationship with the night sky. When you look up, you're not just looking at distant lights, you are looking out from inside a regulated structure. You are living inside a galaxy that has been managing its own extremes for billions of years through nothing more than the laws of physics. It is an island of relative stability in a universe full of chaos, not because someone built a fence, but because the way matter behaves naturally builds buffers, barriers, and filters when conditions are right. The last step in our story is to stitch it all together into one clear picture you can carry with you. 3 shields, 3 threats, 1 galaxy. And one final idea. The invisible structures are not curiosities at the edges of astronomy. They are part of why galaxies like ours can remain organized long enough for planets, chemistry, and eventually minds to appear. So here we are, standing on a planet that thinks it lives in open space, when in reality we live inside layers. Not walls, not magic, layers of behavior. A galaxy is not just stars in a spiral, it is gas in motion. Plasma threaded with magnetic fields. Energy being injected by supernovae, by stellar winds, by the slow breathing of the central black hole. And when you combine those ingredients, you do not get a smooth, evenly mixed soup. You get structure, you get pockets, you get gradients, you get regions that protect other regions not out of mercy, but because physics likes to organize chaos into patterns that can persist. The first shield is almost poetic in how it works. 2 small galaxies should have been stripped bare long ago, but their own motion through danger creates a buffer that slows the danger down. It is the closest thing the universe has to a lesson in resilience. The threat is not removed, it is redirected. The violence is converted into heat, and the heat becomes a cushion, and the cushion becomes time. Time is the real currency of the cosmos. With time, gas can cool, clouds can collapse, stars can form, planets can assemble, chemistry can experiment, evolution can iterate. Without time, everything is just impact and debris. The second shield lives where the galaxy should be at its most unforgiving. The core is a place that should leak radiation like a broken reactor. And yet, the inner Milky Way behaves less like a collapsing disaster zone and more like a regulated furnace. Charged particles get tangled, they wander, they collide, they lose energy locally. The core keeps much of its harshest storm near itself, not because it is polite, but because wind, magnetism, and dense gas are the kind of obstacles charged particles cannot ignore. That is a strange kind of elegance. A galaxy does not need intention to contain its own extremes, it needs structure. And the third shield is the one that reminds you how much we still do not know. The edge of the Milky Way is not an edge like a knife, it is a transition like dusk. And in that dusk, the rules shift again. Incoming particles from the wider universe do not arrive unedited. Outgoing flows do not escape without being shaped. The boundary itself becomes an active region, a mediator between the galaxy and everything outside it. This is what it means to say the Milky Way is an ecosystem, not in the biological sense, but in the system sense. Many processes operating at once, feeding back on each other, producing stability not by freezing change, but by managing it. Now here is the part that is easy to miss if you only take the story as a collection of cool facts. These shields are discoveries, not inventions. For most of human history, we imagined galaxies as simple. Stars, gravity, spiral arms, done. But between the early 2010s and the mid-2020s, multiple lines of evidence began pointing at the same underlying truth. The parts we could see were only the tip of the system. The Milky Way has always been more than its visible light. We did not suddenly gain new shields. We gained new senses. We built instruments that can detect faint ultraviolet signatures of hot gas. We built X-ray telescopes that can trace million-degree plasma. We built gamma-ray observatories that can map the scars cosmic rays carve into interstellar gas. We built detector arrays that can catch the footprints of particles from deep space. And once we had those senses, the galaxy stopped looking like a simple picture and started looking like a living machine made of physics. That shift changes the questions we ask next. How common are Magellanic-style coronas around other satellite galaxies? If they are common, then small galaxies survive longer than older models assumed, and the timelines of galaxy growth change. How exactly does the cosmic ray barrier breathe? When Sagittarius A star becomes more active, does the containment sharpen, expand, or open channels? When it becomes quieter, where does leakage happen? What does that do to star formation and chemistry in the inner disk? What is the true nature of the edge filter? Is it mostly magnetic structure? Is it plasma turbulence? Is it something we have not modelled properly yet? Is there any hint of new physics in how the highest energy particles behave at the boundary between environments? And then the question that always appears when you find three big structures: are there more? Because the Milky Way has other dramatic features we did not even touch deeply here. Giant outflows, enormous bubbles, filaments of magnetized plasma, high-velocity clouds falling in, streams of stars from ancient mergers. Every one of those could hide more regulating behavior, more ways the galaxy keeps itself from becoming either a dead fossil or a chaotic starburst engine that burns out too quickly. The calmest possible conclusion is also the most mind-bending. You've been living inside these systems your entire life. Every human who ever looked up at the night sky looked out through them without knowing. They were in place before Earth formed. They will remain long after. So the next time you see the Milky Way overhead, try to hold two ideas in your mind at once. First, it is dangerous. The universe is full of radiation and violence and slow erosion. Second, it is stable enough for us to be here. Not because it is gentle, but because the laws of nature create buffers when conditions are right. They create structures that turn runaway problems into manageable flows. In a way, these shields are the galaxy doing what every successful system does. They keep the extremes from spilling everywhere. They localize damage. They regulate exchange with the outside. They stretch time. And time, in the end, is what lets the universe do its strangest trick. It takes hydrogen, emptiness, and simple forces, and given enough patience, it produces stars, planets, oceans, cells, minds, and a species that can finally notice the invisible architecture holding its home together.